Lisa Su for the first talk on innovation for the next decade of compute efficiency. Lisa Su is Chair and Chief Executive Officer of AMD. Over the course of her 9-year tenure as the CEO of AMD, Lisa Su has transformed the company into the high-performance and adaptive computing leader and one of the fastest-growing semiconductor companies in the world. She's an IEEE Fellow, a member of the National Academy of Engineering, and was recognized by the IEEE with the highest semiconductor honor, the Robert Noyce Medal. In 2021, Dr. Su was appointed by President Biden to the President's Council of Advisors on Science and Technology. Lisa, you have the floor.
All right, good morning, everyone. It is a real honor and pleasure to be here today to help celebrate the 70th anniversary of ISSCC. And I think the amazing thing is just how much progress has been made over this time period. And it's also great to see everyone in person. It's been a long time to see so many of our industry and academia friends together. So my topic today is about high-performance computing. High-performance computing is something that touches all of our lives in many ways, and it's also what we as an industry and in academia and as an ecosystem are really focused on pushing the envelope on more performance, more compute, more efficiency. So, of course, I have to start with a picture. As they say, a picture is worth 1,000 words or tens of billions of transistors. But as we look at the progress over the last 70 years, you start with sort of the first pocket radio, which had all of 4 transistors. And then the last time I was actually here at ISSCC was actually 10 years ago. We were kind enough to invite me then. And in that time frame, we thought we were making a lot of progress. The state of the art, this is a notebook processor, had just over 1 billion transistors, 4 cores, 4 threads, 32 nanometer SOI technology. And we thought, that was pretty amazing. Now, how many of you were actually here 10 years ago at ISSCC? Actually, that's a pretty good number. That's a pretty good number. So all of you have together helped us get to what we have achieved over the last 10 years. If you look at the state of the art today, it's using a very advanced process technology, significant advanced packaging, chiplet architectures, so on and so forth. Now, this is a state-of-the-art a server processor that has 90 billion transistors, 96 cores, 13 5-nanometer and 6-nanometer chiplets, and a lot of memory. So we have made tremendous progress over the last 10 years. And what I would like to say is that we have so much more to do. Everybody needs high performance and adaptive computing. If you think about all applications, whether you're starting from our personal devices and smart client devices, phones, PCs, tablets, all the way to, I know Eric is going to talk later this morning about 5G and communications and how that drives tremendous processing and horsepower, going to the cloud and high performance supercomputing and everything that we're doing with machine learning and AI. It's on us to continue the trends of increasing performance and capability. And I will say that we've made a lot of progress, but we also have a lot more that we need to do. So taking a look at some of the performance trends over the last decade, this is some data that we've collected, which looks at really industry data. So this is AMD, Intel, all of the processor vendors out there. And you can say that although there are some times that we are above or below the line, in general, we've been increasing the performance trends on the order of doubling every 2 to 2.5 years or so. That is with all of the conversation about Moore's Law slowing and all of the things like that. Even so, there's been tremendous amount of innovation on architecture, on packaging, on other on increasing die sizes, and on power, such that we're able to do that. So this is what we've seen, and that's the same is true for GPU performance. If you look at that over the last 10 plus years, you've seen a doubling of performance every 2 to 2.5 years. So there has been significant improvement there. Now, when you actually put it together, and I like to use this example because it's one of the hardest examples, which is high-performance supercomputing. And if you think about what we're trying to accomplish, we're trying to build the biggest computers in the world for solving some of the hardest scientific problems as well as business problems in the world. And this is how you see where is the state of the art. Like, how hard can you push technology to achieve advancement? And in this case, what we're plotting is over the last 10 plus years, the fastest supercomputers in the world. And what you see is actually, even though on the component basis, so our processors and our GPUs are doubling every 2.5 years, on a system level, when we bring out everything that we have, including much larger systems, much more parallelism, a lot more power capability, a lot more interconnect capability, we're actually able to achieve a doubling almost on an annual basis, which is actually pretty amazing if you think about it. Now, these are not cheap systems. They're not small systems, but they tell you what the technology is capable of if you really bring out every single thing that you know. We just recently passed a very significant milestone last year, which was the first exascale supercomputer. And you can see that there was actually a little bit of distance between that dot and the previous dot. And that exascale computer actually sits at Oak Ridge National Labs, and it's built in partnership between Oak Ridge, HP Enterprise, and AMD. It's using a combination of CPU and GPUs, lots and lots of technology in there, but we were able to achieve an exascale of supercomputing, both from a performance standpoint and, more importantly, from an efficiency standpoint. And now, as we all like to do, we draw the line. We draw the line assuming that, hey, can we keep that pace of innovation going? If we were to do that, what it would say is we would get to a zettascale, or 1,000 times more computing in about the next 10 years, 10 plus or minus. And so that's a challenge. That's a challenge for all of us to think through how might we achieve that. The other thing that's also very exciting that I think is touching all of our lives is just the rate and pace of AI adoption. So I'm sure that everyone in here has used ChatGPT sometime over the last 60 days. Is that true? Everyone? Not everyone's going to admit it, but yes. The truth is, this goes back to the insatiable need for compute. At the end of the day, we have this capability to make our computing much smarter, much more capable, and much more adaptable to the problems that we're trying to solve. But to do that requires that we build more and more powerful computers. So if you just think about these generative AI models, as you increase the number of parameters, your models get better. As you increase the number of parameters, you need much more compute to train and actually to infer as well. So another reason that we need to keep pushing the envelope on computing going forward. Now, I've talked a lot about performance, but the real thing that we have to work on as an ecosystem is actually energy efficiency, because at the end of the day, that is going to be the hardest problem for us to solve. And if you take a look at the same trends now on energy efficiency, and again, this is the same data that we plotted on the performance scale, what it says from an efficiency standpoint, using all of the best technologies out there, our efficiencies are not increasing at the same rate and pace. And there are many good reasons for this, and I'll talk about some of those. But this flattening of the efficiency curve actually becomes the largest challenge that we have to solve, both from a technology standpoint as well as from a sustainability standpoint for our ecosystem. So, taking a look at the same plot on supercomputing usage, if you look backwards over the last 10 plus years, you can see that we have gotten more efficient with our technology. So this is plotting gigaflops per watt versus time for those same largest supercomputers. But it's actually doubling in efficiency only every 2 to 2.5 years, which is different, right? So performance, we were able to improve much faster. Efficiency is actually being limited by some of the physical attributes. And if we, again, draw the line, it would say that for us to get to a zettascale, we would need the machine to be 500 megawatts. That's probably too much. That's probably too much. It's not practical for us to do that. It's on the order of what a nuclear power plant would be. And so this fundamentally says our challenge is to figure out how, over the next decade, we think about compute efficiency as the #1 priority. And there's a lot of work that has been done that will be talked about in this conference that's being done across the industry, but this is the #1 challenge that we have to continue the dramatic increases in performance and capability that we have seen. So some of the reasons that this is hard, and some of the reasons that we need to keep focusing on this. I have to say, process technology is still very, very important. I started when I was a student in process technology and device design, and it continues to be very important. But the fact is, Moore's law has slowed down. It is becoming much, much harder to get density, performance, as well as efficiency. You can see over the last few years, we used to be on a trend of doubling performance about every 3 to 3.5 years. And as we get into the advanced nodes with 5 and 4 nanometer technology going to 3 and 2, we still see improvements, but those improvements are at a much slower pace. And so this is one of the reasons that the energy efficiency is a key, is slowing down. Another reason is, I/O don't scale. They don't scale the way our logic scales. We have made good progress in reducing energy per bit, but when you look at it from an overall channel quality standpoint, it's over much shorter distances. And if you think about our systems are getting much longer, much larger, this ends up being a power limiter as well. And then you look at memory, and we're going to talk a lot. I know you'll have in the session a lot of conversation about new memory, how we bring compute and memory closer together. It is also around the fact that we need more memory. These data sets are getting larger, and the bandwidth that we're requiring makes the memory access power another key area that needs innovation. So if you take a step back, what do we need to do over the next decade? It's really driving system-level efficiency holistically. So thinking about all of the elements across computation, across communications, and across memory that will enable us to achieve the most efficient systems. So one of the most important areas, and probably the area that we focus the most on at AMD, is efficiency through advanced architecture. And there are lots of techniques for doing this, but in terms of the highest order bit is that we want to use the right compute technology for the right workload. And if you think about this whole conversation about heterogeneous architectures or accelerated computing, that's really what we're trying to do. This is an example of that exaflop supercomputer that I mentioned is using MI250, which is one of our newest processors on the acceleration side, and it's exploiting a significant amount of architectural innovation, packaging, silicon trends, to really try to improve the efficiency over time. And so when you look at some of the components of that, it says that we have to focus on everything. And so, with MI250 as an example, it's a 6-nanometer GPU. It has significant new innovation when we compare it versus our previous generation at the same process technology. It has a lot more domain-specific architectural enhancements for both HPC as well as AI workloads. It has higher levels of integration with chiplets and a 2.5D integration, bringing high bandwidth memory close to the compute. And it has the traditional circuit design work that you do in terms of all kinds of power management, all kinds of ways to optimize the design efficiency. And you can see that each of those components is quite important for us to improve the efficiency of the overall solution. And I'll talk a little bit more about each of these components and where we think they really shine. Probably the largest lever in recent times has been the use of advanced packaging and the use of chiplets. You can see that there has been a very nice progression of both capability and payoff with advanced packaging, starting first with just two-dimensional MCM technology. This is the idea that you're going to use the right process technology for the right elements, and so you need your expensive, dense transistors for the computing elements, and then you need, let's call it less dense, maybe other capabilities for your analog and I/O capability. And what that allows you to do is kind of optimize. So that's sort of the 2D version. If you go to 2.5D, you can bring memory much closer to the GPU. It's very, very common. And then 3D chiplets, I think, are just starting to take off. I would say that it's still early. The technology is still maturing for high volume, but there's tremendous capability when you can stack memory on top of a processor, or when you can stack logic on top of logic. You can see that there would be a tremendous capability here. And just as one example, what it really does is it allows us to bring the components of compute much closer together and reduce the cost of communication. So, thinking about when you had these compute elements on a board and how far they were and how much energy you had to spend communicating between them, now you can have them either on package in a 2D or 2.5D arrangement, or stacked in a 3D arrangement. And you see just a tremendous improvement in overall communication efficiency when you do that. So very, very promising, very important for us as we go forward. Another area that there's been a lot of work and will continue to be a lot of work is with domain-specific computation. This is the idea of using the right math for the right operations. So in this particular case, you can see that as we go from, let's call it your double precision floating point to various other math formats, you just get much more efficient computing. And the killer app here is, of course, machine learning and AI and what we're able to do there. But it'll continue to be important. There'll be more specific acceleration that will be used for various applications as we go forward, because you can do this. And anywhere that you can do this, it will help us get more efficient in the computing overall. So when you bring all of that together, I want to give you one other example of what you can do at the architectural level. And now we take what was in the previous generation exascale computer MI250, and we introduce the next generation, which we call MI300, but this is the next generation of GPU acceleration for both HPC and AI. And you see that with 5-nanometer process technology, with 3D stacking, with actually stacking our cache and fabric die on the bottom, stacking the CPUs and GPUs on top, with new math formats, with a different memory architecture, you can see improvements on the order of 5 to 8x, whether you're talking about efficiency or you're talking about performance. I think that says a lot about what the technology can do if you put all those pieces together. And just to give you a little bit of a framework of what we're talking about, one of the more traditional ways when you think about how CPUs and GPUs work together, they each have their own, sort of memory cache, and as a result, they really can't share data across them without going through the processor again. When you use these new architectural capabilities in a stacked format, you can actually have a unified memory architecture so that depending on what you're trying to do, what your next operation is doing, you can just take your data from a unified memory architecture, which just is much, much more efficient, right? So this is all about how do we get that last bit of efficiency going forward. So with that, we believe architecture, particularly around compute operations, will have a very large impact on future efficiency. And from our calculations, we believe that we can be above the industry rate, even above our earlier projections from several years ago, by combining our architectural innovations together with chiplets and 3D stacking to achieve that. So that gives you one view of what you can do with architecture. Now, there are a lot of really smart people here, and I saw 800 plus students, and so we need you guys to help us with the next set of innovations. I'll talk about some of the ones that are sort of very promising as we look at it from an industry standpoint. I talked about the tighter integration between compute and memory. I think this is always going to be the case. As we think about what we want to do, it really is how do we efficiently connect the two. And so from standard DDR5 going to high bandwidth memory, going to 3D bonding, you can see a significant improvement in efficiency. Now, what we've demonstrated so far is SRAM stacking on compute die, which is great, by the way. We've put that into production, and it has a significant improvement in certain workloads, not in all workloads, but in certain workloads. But there's more opportunity here in terms of stacking, DRAM on compute, stacking other types of memory. Obviously, there's some innovation that needs to happen for that to be the case. But this is one area where there's a lot of opportunity for innovation. We also think there's been a lot of discussion about putting processing in memory. So as a processor person, that seems a little counterintuitive, but it makes a lot of sense if you think about it from a system standpoint. What we want to do is be as efficient as possible, and so there may be some processing operations that can be inserted into the memory, and this is some work that we've been doing in our research team with our partner Samsung, which has shown that with some insertions of some algorithms in the memory component, you can reduce the overall access energy by up to 85%. So also very promising. The work here is not just obviously on the individual components, but it's also how applications would use such technology. And so this is an area where a lot of cross-functional learning would need to happen. Also improving the efficiency of I/O. I saw that, Pete, on your list of many things that are being worked on this conference. We believe that a lot of work has been done on sort of the local communication. So a lot of the chiplet work, advanced packaging work, does very well on local communication. But a lot more needs to be done on the longer reach I/O capabilities. And so, optical communication is a key area that we think is very, very important for us to reach anything like a zettascale type computing capability. There's a lot of work that's going on at this conference. We've also been doing some work with DARPA on how to do some of these co-packaged optics solutions as well. But what we like to say is that this is the view of, sort of a future system and package. So one of the things that we are starting to really embrace as an industry is that, the package is sort of the new motherboard. You used to put all of these pieces, taking all of these pieces from different vendors and different technologies and putting it together on a board. Now what we have to do is ensure that there's a way to put all of these different pieces and all of these different capabilities in a package. And what that does is that requires us to think differently on many levels, right? Certainly from the compute standpoint, our goal would be to optimize every one of those compute cores to be the best they can possibly be. So whether it's a CPU or a GPU or a domain-specific accelerator, whether you're going to use an ASIC to do some machine learning, either training or inference, you can have each one of those compute cores be optimized, but they should be able to be optimized by different people. So this whole importance of standardizing chip-to-chip interfaces such that we can mix and match components, I think is very important. And then we talked about, adding, sort of co-packaged optics that can then go across the system overall. And all of this is made capable with, our advanced 2.5D and 3D packaging. So there's a lot of work that needs to be done to enable this, but it is surely doable as we, focus on the right elements of both very clear optimization within each of our specialties, as well as ensuring that there are good enough standards for us to connect to across the different components. So now let's go back to our how do we achieve zettascale computing. I would say that I'm not sure we know yet. I would say we have very many pieces that we talked about. We'll continue to want to push process technology. We continue to want to push architectural optimizations. We'll continue all of the chiplet and memory and interconnect things that we can see today. And we believe that that will significantly enhance our overall efficiency. But if you really think about it, there's probably still a gap because of all of these physical limitations that we talked about. Whether the gap is, an order of magnitude, or it's less than that, or more than that, it's kind of hard to predict right now because there's still a lot of technology innovation to go. But I think it's fair to say that there's still much more we should do in terms of focusing on energy efficiency going forward. And so one of the key things that we should consider is leveraging AI much, much more holistically. And you can think of AI as a solution for, sort of very repetitive problems. And that's the, sort of the training of large models and things like that. But you can also think about AI in much more of a hybrid mode of operation. And just taking a look at the relative performance over the last 10 years, as much as we've improved in sort of the traditional metrics around spec-int rate or flops, the AI flops have improved much faster. And they've improved much faster because we've had all of these mixed precision capabilities that we've introduced there. And so the point is, how do we now use this much more broadly across a number of different problems? One that we're looking at and we think is very important is the idea of AI surrogate physics models. And the thought process again is how do we use the right type of compute for the right problem? And so this is one way of thinking about it. When you think about some of the most complex physics problems that you have out there, how do you solve it? Yes, you can get a big supercomputer and you can run your CFD models and do that with very large data sets. That's the traditional way of doing it. But much more, this concept of AI-accelerated HPC is also a very interesting lever, which is the idea that you might do a part of the physics capability with traditional HPC computing, and then you actually train on that data, and then you can infer on that data so that you can shorten the cycles. And then you might not be at the right answer yet, and so you would go and train on a different set of, presumably, a smaller subset of the modeling. And so this is more of a hybrid workflow. It's early. There's a lot of work to be done in the algorithms here, and there's a lot of work to be done in just how do you partition the problems. But this is a huge opportunity for us to bring now much more algorithmic thinking into our system-level optimization. And if you think about how we get to some of these numbers, we have to do that. So when we take sort of the overall picture, I think the key point, and for all of us who are here, maybe it'll be interesting to see what do we say at the 80th anniversary of ISSCC. Do we have some new elements to talk about? But certainly, if we look at everything that we've talked about, there's significant work going on, tremendous innovation. It's important that we bring it all together to solve large-scale system-level problems. And AI will continue to be a more and more important piece of that, whether you're talking about some of the algorithm work that I talked about, or actually even how we use AI in our design environments to design faster and faster chips, reducing time to market, improving the capabilities. There's a lot of leverage there. So let me finish off by saying, again, it's really an honor to be here. I like to think of coming to ISSCC is like coming to talk to the smartest people on the planet, and so to leave you with anything is really an honor. There's a few things that we should feel really good about, right? We are probably in the most exciting time there is for technology. I certainly like to say in the computing world, everybody needs more compute. Like, people used to ask, well, do I really need more? The answer is yes. You need more and more and more because you can see how much smarter we can make everything that we do and how much more efficient we can make our lives. Even if we have someone who's, I guess for the academics in the audience, you probably don't want your students writing their papers with ChatGPT, but they can probably at least start with it, and then they could make it much, 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 much better because they can spend incrementally less time on the things that are most differentiating. The primary thing that we have to deal with for those of us in hardware is energy efficiency. That is the primary limiter, and that will continue to be the challenge that we should all keep in front of us. We must also innovate in new dimensions. Anantha asked me to say just a couple of words about some of the work that we did as part of PCAST. We were fortunate enough earlier last year to spend some time on what should be sort of the 5 to 10 year vision for the U.S. around semiconductor R&D. And I think the major point is we need all of our disciplines to work very closely together. There isn't one bullet is going to help us get to the next point. There is architectural work to be done, there's materials work to be done, there's systems work to be done, there's process technology, circuits, and the more that we can bring these together in turn to solve large problems, large grand challenges, as we'd like to say, because it brings out the best in the industry and the academia ecosystem when we point to something. So whether it's how do we get to a zettascale faster, or how do we take our current chip design and reduce the time to design a chip to 1/10 or 1/100th of how long it takes? Instead of 1,000 engineers, can we do it with, 10 engineers? Maybe not. But those are the types of problems that, as we think about them, will cause us to come up with the next set of innovations. So again, thank you very much for having me here today. It was a pleasure to be here. And thanks for all that you're doing to keep moving our technology forward.